In this video, I'm going to be discussing the laboratory procedure of recrystallization, and I'll start with the background of how it works and what it's used for and why it works. So to begin with, you take a substance, an organic substance, which exists in crystalline form, and you dissolve it into a solvent to form a solution. And when we do that, of course, the solid crystal diffuses apart into individual molecules that are floating around surrounded by solvent molecules. So these are your solute molecules with these triangular shapes. Now, in most cases, if you were to continue to add more and more solid solute, this solution becomes more and more concentrated. You get more of these solute particles in solution. And remember, particles always attract each other. These solute particles attract each other either by van der Waals, by London dispersion forces, or dipole-dipole interactions, or hydrogen bonds, or some combination of those. And as you add more and more solute, these things tend to get closer and closer together. They interact more often. And eventually you reach a point of saturation. And at that point, these things begin to clump together, to stick together by those attractive forces. And more of these things will stick together, these particles, until you begin to see big enough particles. The solution will start to get cloudy, and you'll get precipitation. And really, actually, as you add these things, it'll just appear you'll reach a point where the solid pieces that you're adding just sink to the bottom, and so you'll have solid solute accumulating on the bottom of the container, like so. But what's really happening here is this continues to dissociate into the individual particles, but at the same time the individual particles are recombining to form solids. So there's a dynamic equilibrium between the particles in solution, the individual particles in solution, and the particles that are stuck together in the solid phase. And so what you see in a saturated solution is just some solid on the bottom. Sometimes it's cloudy up here, but the cloudiness generally settles out and you see solid solute on the bottom. Now, in most cases, solubility of solid solutes in liquid solutions increases with increasing temperature. So in this procedure, we take advantage of that fact. We're going to heat this up over a burner. And since the solubility is increasing, that is going to drive these solid particles apart again. They'll redissolve into the solution phase, and now we've got a much more concentrated solution at a higher temperature. If you do this well, ideally you're going to get a saturated. At this point, it's a good idea. The solution might be saturated. It might not be. We can add a little bit more solute to make sure that it is. And what we normally do is bring this up to boiling, add a little bit more solute till we're certain that it's saturated. And then maybe add a little bit more solvent till it's like a titration. You add a little bit more solvent until you've added just enough that all of the solute dissolves. You've got a saturated solution, that is, at the boiling point of the solvent or of the solution. And then you allow it to cool. And of course, what happens when it cools is that the solubility falls. The solubility decreases in the cooler solution. So these concentrated particles begin to agglomerate again, begin to form solid particles, begin to stick together, and you reform the solid. That is, you recrystallize. So we began with crystals, we dissolve them, and now we are ending up with crystals. That's why this is called recrystallization. And the way this appears, if it's ideal, is this will get cloudy, and you'll begin to see solid particles form. It's almost like snow. The little particles that fall. Sometimes it's not quite that nice, but eventually you get crystals accumulating on the bottom of the container again, solid crystalline material. So what we're going to do now, so what's the purpose of this? What we're going to do now is assume that this compound was not pure originally. That is, there was at least one impurity or some compound that is not the compound that we want. And I'm going to represent the impurity as these circular molecules. They have a different shape, and therefore different interactions between them as well. So what happens now? We do the same procedure, and the impurity remains in the solution. The point here is that the impurities are not interacting with the solute as the solute interacts with itself. And one way to think about this is that solute particles have a given shape that pack very nicely into a crystal. They tend to exclude molecules that do not have the same shapes and interactions. And so as the crystallization occurs over here, as the recrystallization occurs, the impurities are excluded from the growing crystal as these things begin to agglomerate and precipitate out. Thus, we come to the whole point of recrystallization. This is a very common procedure and a very effective in many cases procedure for purifying organic substances. That's the point of recrystallization. That's essentially how it works. Impurity molecules are excluded as the crystals form out of the saturated solution. So now that you have a background and understanding of the process of recrystallization, I'm now going to discuss the procedure of how you use recrystallization to purify organic substances. The first thing you're going to have to do is find, and this is often the trickiest part of recrystallization, is to find the proper solvent or solvents to use to recrystallize your substance. And this is based largely upon the solubility of your compound. Recall that like dissolves like, meaning that polar compounds tend to dissolve in polar solvents, and nonpolar compounds tend to dissolve in nonpolar solvents. So the way I go about doing this is I take those really the smallest test tubes that we have, and they're about this size. There should be a box of them out in the laboratory. And I add again a BB-sized piece of the compound that you're going to be recrystallizing. And we're talking about 5, 10, maybe 20 maximum milligrams of the compound. And I fill this about 2/3 to 3/4 full, about half a milliliter of the solvent that I'll be testing. So if your compound's polar, it's most likely, of course, going to be soluble in polar solvents. If it's nonpolar, it's most likely to be soluble in nonpolar solvents. What we're really looking for here is a solvent that it's slightly soluble in. And so in more detail, we're going to add the solvent. If at room temperature the solute completely dissolves, and you might want to shake this up a little bit, swirl it around, maybe mix it with the tip of a Pasteur pipette. If it completely dissolves, it's not likely to be a good solvent. It's too soluble. That is, it's so soluble you're not going to get crystals forming. So you can probably safely discard the ones that rapidly dissolve at room temperature completely. What you're looking for is something more along the lines of these two situations here. So these are the three possibilities that you have when you add the solvent to your substance. Some of it might dissolve. The solute diminishes somewhat in size. That means that some of it's dissolving into the solution, but maybe not all of it. Or it may be impossible to tell if anything's dissolving. It appears to be totally insoluble. So in these two situations, the next thing you're going to want to do, and actually before I mention that, I should note here that you want to watch for insoluble impurities. The compounds that you're going to be recrystallizing in the laboratory, the unknowns, will have impurities in many cases added to them. And so those impurities will tend to be insoluble and they won't dissolve at all. So if you see solid, it doesn't necessarily mean that your compound's not dissolving. The impurities that you'll be seeing in the laboratory will be colored. That is, they'll be dark, they'll have color to them, they might be black. In all cases, the unknowns in the compound are the same color as most small organic molecules, and that is colorless. So keep a close eye on this. Just because there's solid down here doesn't mean that your compound isn't dissolving. So watch out for impurities. So in these two situations where some or maybe none of the solid solute appears to dissolve, you're going to take the test tube and heat to boiling. So let's scroll up here. So we take the test tubes and stick them test tubes. And I like doing this with several solvents at once. That saves time. It's easy to keep an eye on a number of these at the same time. You're going to stick those test tubes into a sand bath and heat them up until they boil. You might want to stick a little piece of a toothpick into these to prevent them from bumping. So you heat these to boiling and then allow them to cool. And it might be easier to take them out of the sand bath to watch them cool. And once again, there are three possibilities. First possibility is that really nothing did dissolve. So when this is boiling, there was no change in the size of your solute, and as this cools down, you don't see anything happening. So in this case, you have the opposite problem to what we saw when everything dissolved, and that is that the compound is just too insoluble in this particular solvent, so we can't use this solvent for that particular compound, for that solute. Another possibility is that it all dissolved at the high temperature, and you let it cool and nothing tends to happen. In this case here, it's a good idea to take a glass Pasteur pipette and scratch the side of the inside of the test tube here. That leads to little tiny places on the glass, little scratches, for example, where crystal nucleation can occur, or crystals. It gives a place for the crystals to begin forming. You might see crystallization occur in that case. If you don't, that's an indication that you had too much solvent, and you can redo this by adding a little bit more solute. That is, you never really reach saturation. The solution wasn't really saturated. So add more solute, reheat it, and then allow it to cool, and watch for crystallization. The ideal situation is this. We've taken the test tube, we've heated it up, it dissolved, and then as it cools, you see, and it often looks like snow that's forming in here. You see crystals forming inside the test tube. This is what you're looking for. This is when you have a good solvent. The reason I drew two test tubes here is that maybe you didn't have enough solute or enough solvent in this test tube to dissolve all the solute. That's okay. When you redo this at the preparative scale, you'll just add more solvent to get it to all dissolve. So you might have some undissolved solute remaining, but you see crystals forming. So that's a good sign. Or it may have all dissolved, and as it cools, you get this snowy precipitation of crystals. And in either case, you have a good solvent. That's a good solvent to use for your recrystallization. Now, unfortunately, in some cases, you're going to have this situation right here. That is, the compound's too insoluble in all of your solvents and all the solvents that are available. And this situation right here. So in other words, you put your compound into some solvent, some of the available solvents, and it completely dissolves. In all of the other solvents, it doesn't dissolve at all, even at high temperature, even when it's boiling. So you never see crystallization. In those cases, if you're one of the unfortunate people that has one of those samples, you have to try a solvent system that is a mixture of solvents, and that's the next thing I'm going to discuss. So recall that the goal of finding a solvent, or a recrystallization solvent, is you're looking for a solvent in which your compound is soluble only at high temperatures, only when the solution is warm to hot or boiling. If it's really soluble at cool temperatures, it's too soluble, you'll never get crystals. And if it's insoluble, you can't get crystals because it has to dissolve at some point. Now, in some cases, you're not going to be able to find a single solvent where that's the case. In those cases, you use solvent pairs. So the way you use the solvent pair is you take a sample of the compound to be recrystallized, you put it in your test tube, and you add the first solvent. And you want to add a small amount of that. The first solvent is the one in which your compound is freely soluble. That is, that dissolves easily at room temperature. So you add a little bit, really the minimum amount of that solvent that allows your compound to dissolve. That's usually just a few drops because it's very soluble in that solvent. Once it's dissolved, you add a few drops of a solvent that your compound is not very soluble in, is insoluble in. And the trick here is that solvent has to be miscible with the first solvent. So they, in other words, have to form a single solution. There can't be a phase boundary here. Common example of a solvent pair used in recrystallization is water, which is very polar, and alcohol, ethanol, which is polar but less polar. So there are some compounds that are soluble in ethanol and not water, and some are soluble in water, not ethanol. So the combination of those two makes a solution where you can get the compound to dissolve and get it saturated depending on the ratio of the two solvents. So you add the second solvent, the solvent in which the compound is insoluble in, and eventually, once you add that, since you're making the solution less and less friendly, the solution will begin to get cloudy. And that cloudiness is an indication that you are near saturation. Actually, you've passed saturation. You're starting to see tiny amounts of precipitate form when it gets cloudy. So stop adding the second solvent at that point. This is a good point to heat the solution, because remember, the solubility is going to increase at higher temperature. So you're at a little bit past saturation here. So you're going to put this back into your sand bath, heat it up to boiling. It should all dissolve because you were close to saturation at room temperature here. So we heat it up to boiling. And what I would do at this point is add more of solvent 2. So you want to add more of solvent 2 until you it's like a titration again. You're doing this dropwise until you just get back to that point where you're starting to see a little bit of precipitation occur, a little bit of cloudiness here. So you've just gone beyond saturation because you're beginning to see a tiny amount of precipitation. Add one more drop of solvent, 1 to it, and that should, if you're very close to saturation, that should clear this up. Now you're very, very close to a saturated solution. You take the test tube out of the sand bath and allow it to cool. If you are near saturation, you should see crystallization at this point. And that is how you use a pair of solvents to recrystallize a compound. One of the things you'll be graded on in this experiment is the purity of an unknown that you're assigned. And so you're going to have to do this on a larger scale. So you'll use one of your reaction tubes from your microscale kit, and they're about this size. You're going to use about 5,100 milligrams of the unknown compound. You'll have done your solubility test, so you'll know what solvent to use or solvent system. And you'll want to dissolve your compound, so you add a little bit of the solvent. And you'll want to use a boiling chip here because at this scale, when these things pump, you can lose a lot of your product and they can make a mess. You're going to heat the solution up in the sand bath and try to get all of this to dissolve. Now, ideally at this point, you would titrate this until you just added enough of your solvent to completely dissolve all of your unknown compound here. But unfortunately, these unknowns are often contaminated with insoluble solutes, and so there might be little colored particles in here that aren't going to dissolve, and so you have to separate those. And this is a common problem in laboratories if you got insoluble impurities and you're trying to purify something. So once all of your compounds dissolved, if there are insoluble impurities remaining, you're going to need to filter those. And to do that, we're going to use a Hirsch funnel. So that's in your microscale kit. It's a small conical funnel that will fit right into your small filter flask. You'll hook the filter flask up, make sure you clamp this so it doesn't turn over. Hook the filter flask up to the water aspirator. Very important to put a piece of filter paper. So you're going to cut out a piece of filter paper that fits the little fritted disc in the Hirsch funnel. I've got a guide in the laboratory that you can use to do that. Makes it easy to cut these things out at the right size. And then while this is still boiling hot, you're going to quickly, and this is important, pour this through while the aspirator is on. If you do this slowly, if this is close to saturation, you're going to get your compound crystallizing on the piece of filter paper. It will crystallize in the stem of the filter funnel, and it will crystallize as it comes through here. So it's hard to avoid crystallization because this thing's going to be cooling as soon as you take it out of the sand bath. And as you're pulling this through, it's going into a vacuum and some of the solvent's evaporating. That also decreases the temperature of the solution, causing even more recrystallization to occur. So to prevent losing lots of your product, lots of your unknown in this filtration, it might be a good idea to add a little bit extra solvent here to make it to get to the point where it's not as close to saturation. And if you have some crystallization here, you can have some hot boiling solvent nearby, and you can kind of rinse that through with little drops with a Pasteur pipette of boiling solvent so that you don't lose too much product in the filtration. So once you filter this, it's a simple matter of pouring this back into a clean reaction tube. And if it cooled down and you didn't get crystals, which is unlikely, then you'll probably have crystals down here. You'll need to scrape those in. Pour the liquid in and scrape those in. You've got a solution that is it's really a mixture of your crystallized product and solution, saturated solution at that point. You heat this up to boiling till it all dissolves again. If it doesn't all dissolve, you titrate it by adding more drops of solvent, and then allow it to cool. If you added so much solvent here, hot solvent, that you didn't get crystal formation. That is, this is all now the filtrate down here is all liquid. That means that it, of course, isn't saturated. And so you're going to have to boil some of this off over here gently, again with a boiling chip. So that's something you may have to do, boil some of it down, maybe boil about half of it off, and then allow it to cool. And if you still don't get crystals, you have to boil more off. But at some point, you'll get to the point where it's saturated. So once you're confident this is saturated, take it out, put it in a test tube rack or put it in a beaker and just let it sit. You want it to cool slowly. Cooling slowly tends to lead to the formation of larger crystals. Also, you don't want to disturb it. If you shake this up or move it around a lot, that tends to make smaller crystals. Large, slowly forming crystals tend to exclude impurities better than smaller crystals that form more rapidly. So you want the crystals to form slowly and be relatively large in size. You want really nice, large, big crystals. And again, as we mentioned previously, if you don't get crystal formation, you're fairly certain that your solution was saturated as this is cooling. The first thing to try here is scratching the inside of this with I usually use the stem of a glass Pasteur pipette. That leads to little tiny scratches in the glass that are nucleation spots for crystal formation to begin, and often you'll see crystals forming rapidly when that happens. If that doesn't happen, you can try cooling it in ice bath. That further reduces the solubility and can tend to lead to crystal formation. And if that still doesn't work and you're certain that your solvent worked well, following the procedure above for finding a good solvent for recrystallization, you probably have to boil even more of the solvent off to get crystallization to occur. It's still not saturated. Another thing I should mention here, sometimes you have soluble impurities that are colored. Colored compounds tend to be bigger molecules, and often one good way of removing colored compounds from solutions is by adding activated carbon. That tends to bind to a lot of colored compounds. And so if you have a solution here that's colored at this point, before you filter out any of the solid impurity, going back to originally dissolving your compound, if the solution is colored, try adding a small amount, usually about 1%, or really more like 0.1% by mass, of the activated carbon. It's a very small amount. You don't want to add too much activated carbon because activated carbon can also adsorb your solute or the compound you're trying to recrystallize, so you want to use a very small amount. Boil it with the activated carbon and filter the activated carbon out as you would insoluble impurities. So the filtration in that case is taking care of two things, getting out the activated carbon and it's removing any insoluble impurities. And so that's one way of getting rid of, in some cases, of getting rid of colored compounds, colored impurities from a solution. One other problem you may run into is what's known as oiling out, and that is when you're cooling your solution, instead of getting crystals forming, you get an oil. And this can be a really aggravating problem. So I'm going to discuss now what to do in those situations. Oils most commonly tend to form when the solution that you're recrystallizing your compound, your solute from, attains a temperature that's higher than the melting point of your solute. And so as it cools down, you get, instead of a nice crystal formation, you get oils forming. That's not the only time that oils form, but that's commonly what happens. So one way of avoiding that is to add more solvent to the solution when it's boiling. That gets you a little bit away from saturation when it's boiling, but that reduces the boiling point of the solution because a more dilute solution has a smaller boiling point elevation. And so hopefully that will bring you down below the boiling point or the melting point of your solute and will avoid the problem of formation of oils. Oils tend to be a particular problem when you're using solvent pairs. So one strategy to prevent oil formation when you're using solvent pairs is to change the ratio of the solvents in the solvent pairs. Again, that will change the boiling point of the solution. Another thing to try, if you begin to see oil formation, is to try to add a seed crystal. So leave a little piece of your solute, a little solid particle of your solute uncrystallized, or leave that out before you do the crystallization, and have that on hand in case you have a problem with oil formation. That Having that seed crystal present as the solution is cooling gives the solute a place to nucleate and tends to cause crystal formation instead of oiling out. One last resort when you have oil forming is a process known as titration. And in that process, in that procedure, you collect the oil, usually using a pasteur pipette. You squirt that out onto a watch glass and add little droplets of water to it and mix it up with a spatula or the tip of a pasteur pipette. And that tends to cause the oil to form solid crystals again. Now those crystals aren't going to be pure because they formed rapidly, and that's the problem with oils. They're not pure either. They come out and they tend to, since they're not packing together in a crystal, they tend to come out of solution with impurities. So once you have reformed a solid with this titration procedure, save some of that crystal. The rest of that crystal you're going to try to recrystallize again, doing one of these things, either using more solvent, trying a different solvent, or changing the ratio of the solvent pair. And once the solution is cooling, add the seed crystal from when you titurated the original oil, encourage crystal formation. So finally, you're going to have to turn in a sample of your purified unknown, and so you'll have to collect the crystals that you form. Two ways of doing that. The first is, again, filtration using the Hirsch funnel, and so just to really quickly go back over that. So that's, again, how you set up the Hirsch funnel with your filter flask. You'll be using the aspirator, only this time you're going to be collecting the crystals here instead of trying to get the crystals to go through and into the filtrate. And so again, always use a piece of filter paper. Pour the solution through. You don't have to do it rapidly this time. I should point out, and I forgot to mention this last time, when you're using the aspirator, it's very important that you do one of two things. Either you have a flow interrupter in the line that goes to the aspirator, and I can show you how to set that up. Or before you turn the water off in the aspirator, you pull the top off this to release the vacuum. Or another thing you can try is turning the aspirator off very, very slowly. If you turn the aspirator off rapidly, there's a vacuum in here, and the lack of pressure here will draw water back in. And when you're collecting your crystals at the end, that's not a problem. But if you're doing this when you want to filtrate, that is when you're filtering off earlier, when you're filtering out the insoluble impurities, pulling a lot of water in here is going to ruin your experiment, because this is what you want. It's the filtrate that you want. So whenever you're doing a vacuum filtration with a water aspirator, you either unplug this first or turn it off very, very slowly. So those are probably the two best things to do. So the other possibility for collecting the crystals is simply removing the solvent from the reaction tube using a long-stemmed pasteur pipette. Now, it's for this reason, for this purpose, that it's a better idea to use the reaction tubes from your microscale kit than it is test tubes, because the reaction tubes in your microscale kit are designed for this. That is, they have a flat bottom at the very bottom of the tube that enables you to put the tip of a long-stem pasteur pipette right down flush with the bottom. And when the tip is flush with the bottom, that prevents the crystals from being pulled up with the solvent into the pasteur pipette. So you draw the solvent up while the tip's right flush with the bottom, take the pasteur pipette out, and of course get rid of the solvent, the filtrate. Now, if you do it this way, in fact, if you do it either way, you're going to want to wash your crystals with just a few drops, 2 or 3 times, a couple of times, of cold solvent. That removes any impurities from the crystals. One more thing that you can do here to really dry these crystals off is to, and I'll show you how to do this in the laboratory if you decide to filter this way. You can put a piece of filter over this, put this into a larger test tube. Really, your reaction tube works well, not your reaction tube, your cold finger works well. Turn that upside down and centrifuge it, and that will draw all of the filtrate out away from your crystals. And so with that, you should be ready to do your recrystallization experiment. Let me know if you have any questions, and I will see you in the laboratory.